Collisions happen everywhere at any time. Take a look at this example. Today we'll be talking about collisions, more specifically elastic and inelastic collisions. My name is Carrie Moore, and let's start our morning physics.
Like I mentioned earlier, collisions happen everywhere. It applies to situations or events such as small particles, to balls on a pool table, to even asteroids and planets. Can you believe that? Basically, anything that can collide. An elastic collision can happen. But what exactly is collision? Collision is whenever an object in motion comes into contact with another object, essentially transferring kinetic energy and momentum. But keep in mind, any collision of linear momentum is always conserved. But due to the different types of collisions, that fact can differ. With that said, let's talk a little about elastic collision. Well, what is it? Elastic collision is essentially a state where there is no net loss in kinetic energy. In other words, when separate objects collide, they separate. Take a pool game, for example. When two of those pool balls collide, they just bounce right off each other. On the other hand, inelastic collision is essentially a type of collision where there is a loss of kinetic energy. In other words, when separate objects collide, they move together. Let's take a car crash as an example. When a car collides with another car, a lot of the times they continue moving in the same direction together. Since these two collisions are different, there are, of course, some key differences to always remember. First, elastic collision causes the total energy of momentum to be conserved. This means, since there is no loss in kinetic energy, the objects will bounce right off each other. On the other hand, inelastic collision causes the total momentum to be conserved, but the kinetic energy to not be conserved. This happens because kinetic energy can be converted into either sound energy, heat, or internal energy. That's why I use the car crash as an example, because when a car crashes, the first thing we tend to see is, or hear in this case, is the sound of it crashing, which can be very loud. With that all said, there are, of course, types of elastic and inelastic collisions that we call perfectly elastic or perfectly inelastic collisions. Well, what are they? Perfectly inelastic collisions are essentially separate objects colliding and becoming one mass. For example, when asteroids collide, they fuse together and become one object. With that in mind, when examining perfectly inelastic collisions, it's easy to analyze their momentum. This is because when we treat the objects as single objects and add them together, we can find their momentum. This is demonstrated by the expression m1v1 plus m2v2 equals m1 plus m2 all times by vf, where vf is the vector sum of two velocities. On the other hand, perfectly elastic collision is the opposite of basically perfectly elastic collision, where instead of separate objects becoming one mass, they just stay as separate masses.
Now, let's put what we learned into practice.
For this example, a 15 kilogram toy car is moving east at 18 miles per second and collides with a 12 kilogram toy car at rest. The toy cars stick together. So basically, after their collisions, they are stuck together. What is the final speed of the two toy cars? So, in this problem, we're trying to find the final speed of the two toy cars. Total momentum equals total momentum. Just like I said before, it's the total momentum before the collision equals the total momentum after the collision. So let's make this our mass 1, then our mass 2. We'll say this one is the 15 kilogram car, while this one is the 12 kilogram car. This is what we would call an inelastic collision, because based off of the definition, inelastic collisions stick together and become one, just like in this picture. To find VF, let's use the equation for this. So that equation would be, again, m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. We're not looking for the two velocities. Instead, we're looking for their final velocity of both of them, because we already have their initial, so we need their final. So with that said, we can simplify this into another formula, which will be m1 v1 plus m2 v2 equals our final velocity m1 plus m2, because we're looking for both of them, which is why we put it like this. So let's write down what we do know, even though we kind of already have it. We have our mass 1, which is 15 kilograms. We have our mass 2, which is 12 kilograms. Now we just need, again, to find their, we also have their velocities. So we have our mass, V1 is going 18 miles per second, and our second velocity is at rest, so it's 0 miles per second. So with that said, let's plug everything into our formula so we know what we have. We have 15 times 18 plus mass 2, which is 12, times 0 equals VF 15 plus 12. Let's solve for everything that we have. By doing that, we're going to have to distribute this. So we'll have 270 plus 0 equals 12 VF plus 15 VF, which equals 270 equals 27 VF. Now, all we have to do is solve for VF by just dividing 27, cross that out, and then VF, our final velocity, will equal 10 miles per second. Now, how do we know if this is right? When our mass increases, our speed will decrease. In order to prove to see if our answer is somewhat correct, well, where do we start? We knew our mass started at 18 miles per second. Then our final speed was 10 miles per second. But then our second started from 0 and ended at 12, because remember, this is the final speed for both of them. Why is it that this one started to kind of speed up? Well, think of it like this. When two objects come together, when one object hits another object at rest, that momentum will cause it to transfer kinetic energy, causing this one to move. That's it for this question.